Hello everyone. So we are finally back with MIFMO 2026 problem 4. And I know that this video took like 3 months to film. As you saw from the vlog, our university's team went to the Olympiad in Vienna and we got quite good results there. I personally got a silver and I think our team performed quite well. And still, we need to finish with the MIFMO Olympiad, and only then can we proceed about the exact problems of the Vienna Math Competition. Okay, so let's read through the statement. We are given two matrices, A and B, 2 by 2 matrices to be exact, and they have integer entries. And in addition, A plus B, A plus 2B, A plus 3B, A plus 4B are all invertible matrices. This is important, whose inverses have integer entries. And this also sounds important. And we need to show that if we have these 5 conditions, then it implies that for all t, the matrices are invertible, with integer entries, of course. So yeah, this problem is by far the most difficult one. I don't know if you remember the prior problems, but all of them, problem 1, problem 2, problem 3, are all very routine. There's not much thinking, especially in problem 3, the integral one. You just apply the u substitution and that's it. Something that you'd see in an actual handbook, a textbook. Problem 1 and 2 require somewhat more thought, but they are still pretty standard. And maybe they require more thought, but they are still quite easy. This problem requires a lot of more knowledge, and yeah, I'll elaborate maybe in the end. So yes, let's try to understand everything that is being said. So we have some matrix A. Let it be A, B, C, and D. I know there are more standard notations, but for me this is more simple. And matrix B, let it be E, F, G, H. Right? And we know that since these matrices have integer entries, we know that all of these numbers are integers, right? Not necessarily positive, not necessarily negative, maybe even 0, but who cares? That is not given, and we can't really figure this out yet. And we know that these matrices, A plus A, A plus B, A plus 2B, A plus 3B, A plus 4B, okay, I guess we'll have to stick with it, are invertible, and the inverse has integer entries. So, okay, well, we know the inverse of a matrix, right? If we have some matrix X, okay, let's say A, right? The inverse of matrix A is what? It would be I don't know how to say, I'll just write out the formula, but it would be dA minus C minus B divided by the determinant of A, which is non-zero because if it were 0, the matrix A wouldn't be invertible. And yeah, this formula is pretty standard. You just you swap these around, and you swap these around and add a minus. If you multiplied everything out, it would cancel out nicely, and you'd get that this is equal to 1, I think. Right? Yeah, right. Okay, so from this, and once again, just to make things clearly, I'm presenting my own solution. Even though my solution is kind of similar to the official one, but I think it's just everything flows nicely. So yeah, this is a very standard formula known in linear algebra, or just with matrices, when dealing with matrices. So okay, but wait, now we can do the same thing for all the matrices, right? So let's define. We know that for all t, or maybe I just proceed here. No, I think it's okay. Maybe we can even do it like this, or maybe no. Let's do it in the general case. So we know that the same formula would hold for a plus b, a plus 2b, a plus 3b, a plus 4b, and in general, a plus tb minus 1 would be what? It would be d plus th. I don't really have much space here. It would be d plus th, right? Because t times this, and since you swap this around, it comes here. Or maybe I'll just write out the a plus tb matrix would look like a plus te. Here we would have b plus tf, c plus tg, and d plus th. So the inverse of this would what? Swap these around, so we get this. And here we'd get minus c minus tg, and here we'd get minus b minus tf. And once again, divided by the determinant of a plus tb. Okay, but now we can notice an interesting thing. Of course, this is just for 0, only for these t. And we need to prove that these imply that this holds for all t. But this is, of course, not proven yet, and we need to prove this. Okay, so how can we proceed? Well, now we look at one very, very interesting thing. Basically, what we can find is that all of these, we get a matrix, right? When we divide by this determinant, we also get a matrix. But we know that this matrix has integer entries. So we know that determinant of a plus tb divides all of these entries. It divides d plus th, right? It divides c plus tg. It divides b plus tf. And it divides a plus te. I didn't write the minus signs because it doesn't make a difference. Right? We get this. But now, look, there's a very interesting thing happening here. What if we try to write out wow, that was a stutter and a half. What if we try to write out the determinant in general? Well, the determinant of this matrix, right, or just denoted by this, would be A plus TE. I'm still thinking about that stutter. B plus TF and C plus TG, right? This would equate to A plus TE times D plus TH minus B plus TF times C plus TG, right? The product of these minus the product of these. And now this is where I think the ability of why this problem seems intuitive to me, because at this point we are basically done with all the university knowledge, all the algebraic, all the determinant, all the matrix stuff. Now it's basically just pure numerical manipulation. So look at what we get exactly. We have that this determinant, I'd like a different color. Where can I get a different color? This is very important. We get that this determinant divides all of these terms, but the determinant itself is composed of these terms. So something here seems very bounded. We just need to find what exactly it is, and we'll be done. So, okay, now we can proceed, but basically, look, since the determinant divides this, what happens if we multiply these two together? Let's say, oh, we want to construct the same thing. So if determinant divides this and determinant divides this, so determinant squared would divide their product. Times A plus TE, right? But it would also divide their product by the same exact claim. But if we know the fact that it divides these two numbers, it also divides their difference. Divides their difference, divides A plus TE times D plus TH. I think you're already seeing what I'm seeing. C plus TG, which is just the determinant of A plus TB. And now we have a very interesting thing. Square of some number, and we know that the determinant is an integer, because what? The determinant is a product of this. This is an integer, this is an integer, this is an integer, this is an integer. So the number itself must be an integer. So what we get is, we get that n squared divides n. Or in other words, n divided by n squared must be an integer. That seems very interesting, right? In addition, we know that we can't have any degenerate cases And determinant can be equal to 0. Why is that? Because if it were equal to 0, we wouldn't have an inverse matrix. So since basically we can divide by n because n is non-zero. So we need this number to be an integer. And I think all of you see that this only can happen if n comes from this set. I don't know why I chose n, but I think it's maybe more intuitive to see this in n, not just some random determinant. So yes, we've shown that the determinant of these matrices comes from the set -1 and 1. And I think this is the point where my solution comes back to the official solution. But look, what exactly is a determinant? This is the determinant, right? But if we multiply these things together, we get what? We get AD plus TED plus TED plus, wait, I'm struggling, plus ATH plus T squared EH minus BC minus BTFC minus minus TFC. No, yes. No, I made a mistake here. Minus B. Oh, this is incorrect. This is very incorrect. Okay. Let's fix this. Okay, so minus BC, minus BC, minus BTG, minus BC, minus BTG, minus TFC, and minus T squared FG. And it's interesting what we have here, because, okay, I'll rewrite the terms. I'll group the terms. We get T squared EH minus FG plus TED plus AH minus AC. No, I think this is once again some mistake. ED plus HAH minus BG minus FC plus AD minus EC. Finally, okay, and now I think this is one of the, no, I think this was the most beautiful part, but this is the second most beautiful part. This determinant, right? Since these determinants, most of the time we view it as like some random thing that's doesn't even know what we don't really know what it exactly is. But right now, this determinant is just a function of t, right? Because these are given, since they are integer, since they are entries of the original matrices, these are given, these are given. So we have some quadratic equation, at most quadratic equation in t. And this is where one of the nicest parts in the solution comes from. I'm saying that the third time already, but this implies that, what does it imply? Okay, since we know that this equation holds for at least 5t, right? 0, 1, 2, 3, 4. Basically, So okay, there's this thing called pigeonhole principle, which basically is a smart way of saying that if you have n boxes and you're trying to put n plus 1 pigeons into these n boxes, there will exist some box that will have at least 2 pigeons, which is just intuitive, right? Because you can't have, all boxes can have less than or equal to 1 because, yeah. So by the pigeon there, so basically this pigeonhole principle comes in handy. Since we know that there exist 5 values, right? And at these 5 values, we can only attain -1 or 1. There exist at least 3 at which these numbers coincide. Trying my best. So basically there exists some T1, T2, T3. All of them are distinct, such that f of T1 equals f of T2 equals f of T3. And this is either -1 or 1. And f means this function. Yeah, we can denote this function as f of t. And now look, if this function, if we had a quadratic function, i.e. this wasn't equal to 0, how would the function look? Well, like this, or like this. Right now I'm just like explaining everything in simple notation. But we can't have the same value at 3 different points. This is never possible. I think this is like known as, like, yeah, you can just, yeah, you need to find the solutions to this, like f of t equals -1 or f of t equals 1. But like this can have like at most degree of f2, f of t like, which is 2. This can have only 2 solutions. So basically what I'm trying to say is that if we have, for example, like x cubed to something, it can never have 4 different, at 4 points it can never attain the same value. Right? I hope you understand. I think it's really intuitive if you give it more thought, because we know how the quadratic looks. It can have, can have something like this. I've already shown it. So we can have a quadratic. Okay, so suppose we have a nonlinear thing. Suppose we have a linear thing. No, we must have a linear thing. So if we have a linear thing, which is non-constant, so what? It would look something like this or like this. But this, once again, could never have 3 different solutions, even more, I think. So this also must be equal to 0. This is minus BGS. This is G. This is B. And this is F. Yeah, I'm sorry. This is B and this is F. Gosh. So this also must be 0. And hence, the whole function is a constant. F is constant. And once again, when I'm saying f, I mean this. But right now, this is yet another beautiful part. What we've shown, we only had that this attainability of 3 is for t between 0 and 4. But look, we've shown that this is 0, and we've shown that this is 0. But previously, to get to this function, we never used the fact that this t is bounded in this interval. No, we didn't. So as a matter of fact, we get that determinant a plus tb, or f of t, is always constant. Is always constant. i.e. -1 or 1. It can't jump even. Either it has to be -1 or 1. It can't be jumping all over these terms. So now if we back up for a second, what did we need to show? We need to show that for each t, the matrix a plus tb is invertible, and that its inverse has integer entries. Okay, so we need to show first invertible, integer entries. I'll write a question mark. Well, the determinant, when is what you call it, a matrix invertible? It is invertible when the determinant is non-zero. And have we shown that? Yes, we have. We have shown that this determinant is either -1 or 1. So this means that this matrix is indeed invertible for all t. For all t that are integers. And the second thing we needed to show is that its inverse has integer entries. Okay, so how does the inverse of this matrix look? A plus tb inverse would be yes, it would be okay, I'll use it like this. A plus tb transposed. Well, I think it has like some, but yeah, transposed, but with I don't know how to say it, but like adjoints maybe. Yeah, when you swap around these and when you add a minus signs to these. And you're dividing by some constant, either plus or -1. So look, a plus tb has integer entries. Right? This is correct. Taking the transposition, so swapping these around and these around, and adding minus signs, still leaves it with integer entries. And finally, dividing by -1 or +1 still leaves it with integer entries. So this means that all entries of this side are integers. And hence, all entries of this side are integers. And thus we've shown that. Yeah, it was a long solution. So now just to quickly reiterate what we've done and why this problem is nice. Well, that's for you to answer, I guess, why this problem is nice, if it's nice for you. So let's briefly go through what we've done. Is we've considered the matrices, right? Then we've shown that. Okay, let me think. Yes. So we know that this determinant is not zero. And then, since it's not zero, we can start off with doing some divisibility tricks. And then you get that the determinant of these must divide all of these terms. But if you explicitly write the determinant out, you get that the determinant is the product of these terms. And then you notice this very strange and very, how do you call it, very bounded looking condition. That the determinant kinda divides itself. And yeah, if you write it out explicitly, you get that the determinant divides all of these terms, so you can multiply them together. These terms, so you can multiply them together. And then, straight up, it implies that their difference is divisible by the square, which is just the determinant itself. So yeah, then we had some manipulation here. We get that. So this is the first major part, getting to here. I think in an Olympiad, this would be worth, I'd say like a 5 or 6 out of 10 points, maybe even 7, because at this point it's, yeah, maybe 6. And then you notice that the determinant is not some random magical, mystical stuff. It's just the function of t. Some weird function, but nevertheless a function. And yeah, then we notice that it can be a quadratic, but because it will never attain 3 points. We then notice that it can be a non-constant linear function, and thus it must be a constant function. And with all of these things together, we get that it is always constant. And then we are simply left to quickly explain why it means that it is invertible and why the entries are integers. Whew. Yeah, that was a solution and a half. So yeah, 3 main parts. Part 1, part 2 maybe, and part 3 something here. And why is the solution nice? Because when you get this problem, you could never guess, at least I personally wouldn't have guessed, like before. I needed like 10 minutes just to quickly understand. After I got this divisibility, I think after you get this and you have this, especially if you have anything up to here, you'll finish the solution. But getting to here and understanding that this is important, this is useful, and this is somehow leading to the solution, it's non-trivial. And why is this problem nice? Because when you get this problem, integers, matrices, entries, invertibility, well, you're planning to use some algebra manipulations, some maybe, I don't know a lot about matrices, but something complicated, something that you can apply it generalized to all t. But at the end of the day, it's just number theory. It's just one simple divisibility trick that you get that the square of a number divides itself, and then some function manipulation that I think you learned this at school, that yeah, you can't have a quadratic going through to 3 of the same points. And yeah, and basically we're done. So yeah, I think all in all, this problem is very beautiful, nice looking. And yeah, so I finished with all of these problems for now. So MIFMO 2026 is done, and the Vienna log is done. So I hope you enjoyed these 4 problems. I hope you understood the solutions, and hopefully, and most likely, we'll continue with the Vienna solutions. Or yeah, if you have any other suggestions, go ahead. Yeah, that's it, and have a nice day.